Hi, this is Fred Glenn, K9SO, and welcome to the introductory session to EZNEC antenna modeling. This isn't intended to make you an expert in EZNEC, but it is intended to answer some questions, some stumbling blocks for some beginners the first time you open up the program. We're going to, in this session, build an antenna model. We're going to show you how to do that. It's just going to be a simple dipole. We're going to model and show how it can predict SWR, azimuth patterns, elevation patterns. And finally, we're going to get into a little bit more complex design, an inverted V and other bent designs. And lastly, we're going to interpret the grounds and vertical models and then compare antennas to optimize your environmental reality. So please open the EZNEC program, and this is your main menu. And I wanted to point out a couple of different things here. So the important things are the wires menu, the sources menu. The wires menu is where you're going to enter the coordinates to begin and end your wires that you're going to draw. The sources menu is the end of your coax. This is the feed point of the antenna. Loads, we can place load coils, traps, and so forth. Transformers. Transformers can be impedance matching transformers, balance, and that kind of thing. Transmission lines, we can connect coaxes, and of course, lastly, loads. Loads can be, as they are intended to be, terminations of everything. So let's just open up a couple of screens here. Let's go to the important one, the wires menu, and this should pop up over here. It's going to show you the dimensions of the coordinates of each end of each wire. Right now, we've only got one wire programmed in, but we're going to get all on the same page. You're probably not going to see the same exact thing as I am. So sources, we're here in the source page. This is going to tell us where we're going to tell the program where to place our sources. And we need to get started by getting everybody on the same page. So let's go to the next slide. The wires menu, submenu, and go to change units. Click there, and now we could choose millimeters, meters, feet, inches, wavelengths, whatever you prefer. For this presentation, I'm going to do this in feet. So let's go over to feet, click OK. And now all of our units, if you notice here, have changed to feet. So let's go to one of the stock. We want to open, go to the open button here on the main menu. Click that, and you should see what we want to open up is BY dipole. I have to find that myself, and I'm going to, this is the BY dipole screen now. You're probably seeing different numbers here because I've already modified it from the stock. So we want to, we're going to want to change some of the parameters here. First of all, before we do that though, we want to display what this antenna looks like. So let's go over here to this button in the left-hand column of the main menu called View Antenna, and click that. And now we have a little description. Now we can actually see what the backyard dipole is. And once we get the yeah, okay. So one thing on this view, if we want to take a real close look, we can go into zoom. So go over here to the zoom slider, and you can kind of expand it. Now, if you noticed, as we expanded it, it went off screen. I can make it any size I want here. But now off screen, we can go down to the move image, and we want to bring it down in the Z direction. So we want to bring it down like this. And now we can zoom in a little bit farther. Bring it down a little bit over to the Z direction, a little bit in the negative Y direction. And you can just kind of experiment with placing the dipole. So when we get into more complicated designs, you're going to want to zoom in to see exactly what kind of connections that you have. For right now, let's go back and reset. Under the zoom button, hit the reset button, and then move image. You also want to reset there. So now everybody should be seeing something similar to this. So let me just go on. Now we're going to we're all going to go get on the same page here. Now what I want you to do.
How'd you get into that one view there? I'm not seeing the. I'm not seeing this part, this menu over here. Can you hear me?
I can hear you. Well, which menu are you not seeing? What's the?
I'm in the view, and on the side where you're zooming up and down, I don't have that on my added on the side there.
You mean this
Yep.
area here?
Yep.
Okay. Well, it's not important for right now, but that's probably, you know, show controls. Do you see this under view and show controls?
Yeah, got it. Okay, thanks.
Okay, so here's the zoom. Once again, you can kind of zoom in, you can lower it or move it, you can go back and forth so that you can do it. And then when you're done, hit both reset buttons and you should get back something like that.
Okay, I got it. Thanks.
So what we're going to do now is everybody's reading something different. I'm reading if you come up here to frequency, you may be seeing something like 299 megahertz or something like that if you've never messed with this. But we want to get all of this on the same, all of us on the same page here. So click the frequency arrow, and this little window should come up. And what we're going to do in the frequency window there, we're going to type 7.1 because we're going to build a dipole that's in the center of the 40 meter band. Then we're going to go over here, hit this little rescale button. Now what this is going to do, it's going to change all of these parameters up here, and we're going to rescale it to 7.1. And let's go up and click. Now we have a 40 meter dipole. Now notice that all these lengths have changed. The frequency has changed. The wavelength is calculated from that now. And all the wires in those dimensions have been changed. So let's just go to, when you do rescale, you end up with lots of digits to the other side of the decimal point. So what I want to do is let's just get some decent numbers in here that we can play with. And we're going to, let me see where that screen is, what I want to change to. So I want to change these numbers. This is how you do this. So before I do that, the wire here, we have one wire in this design, and that's identified by that tiny little thing, number 1 over here that I'm pointing at. And we have end 1 of that wire and end 2 of that wire. Now those are given in the Cartesian coordinates up here, 0, 0, 59. X0, Y0, and Z59. Let's change that up to an even number 60, just so we don't have to deal with all those numbers. And we're going to go over to end 2. We're going to change the Z height to 60 there too, so that we remain horizontal. And for length, let's just choose 66 feet for right now. So everybody should have this on here. End 1 should be 0, 0, 60. That's the X dimension 0, Y coordinate 0, 60. And end 2, which is this point over here, we're at Y 66, X 0, and Z still 60. You can take your you can hit your cursor, press the left button, and you can kind of move the coordinate system around like this, so you can get a little better view. Just put it in a position where you're comfortable. Over here, make sure you have the number 12. You type in the hash 12 if you don't have that showing. Type in 11 here under the number of segments. Those are those tiny little green dots in here. So we want to have 11 segments in this design. Dielectric and thickness don't matter yet, but let's just type in 1 and 0 if you're not showing that. And let's go. So now we have a dipole up 60 feet. And it should be, well, we didn't actually tune it here for 7.1. I just kind of guessed it as overall length of 66 feet. So what we want to do now is start the fun. This is what it's all about. So we want to view the SWR of this antenna. How close are we to our nominal point? So we want to come over here to the main menu again, and we want to hit the SWR button. Now the sweep parameters window should open. What we're going to do is we're going to sweep from a low frequency. This is kind of like your antenna analyzer does. We're going to sweep from one frequency to a higher frequency. And we also have to determine, we have to tell it the number of steps that we want to do. So to begin with, I'm going to start this sweep at 7 megahertz. We're going to sweep it up to 8 megahertz. And we're going to do it in 20 kilohertz steps. That's a 0.02 megahertz. All right. And now we're going to do this. We're going to click, and it's going to think about it for a while. And bang, it's all of a sudden now we have our SWR curve for this dipole. Now, a couple of things I want you to notice. This looks like the resonant point. Let me get up to my screen here. Looks like the resonant point here is at about 7.34 megahertz. Now, this is the detail down here of what you're looking at. So I just clicked on the screen here. You can click anywhere at any frequency on the screen, but I'm going to pick the minimum SWR point. And it shows that it's 7.34, and it says the VSWR is 1.64 at resonance. The impedance is 81.75 plus J 4.2.3, blah, blah, blah. It's very close to resonance. As a matter of fact, you can go in here and you see it change from a minus J to a plus J. So at resonance, this would be 0. It has a reflection coefficient and return loss. And now reflection coefficient and return loss is exactly the same thing as SWR, just a different way of looking at it. So we're only going to concentrate for right now on the SWR that we're all kind of familiar with. So we should be now, what we didn't do though, is that we wanted to resonate over here somewhere at 7.1 megahertz. So if you think about this now, we want to have a lower resonant frequency. We want to move our SWR curve so it resonates at 7.1. So we have to lengthen our antenna somewhat. And we're going to do that. Whoops, excuse me. Let me turn that down. So now this is an iterative process, and I just happen to know what the solution is. So we're going to come up here and change end 2 of our display, and it's going to go to 68 feet. And you click on that. Now our SWR display goes away because it's no longer valid numbers. We've changed all the parameters. So we have to come back in here, resweep, rerun. And there we have it. Our SWR curve is now minimized at 7.1. Like I say, you're going to normally have to go in and try 60, 67, 66 and keep fine tuning that. It's an iterative process. You're going to have to just do that manually. I just happen to know that 68 was the number that we're going to use just to save some time here. Now,
you know, Fred, nobody really works that end of the band.
Right. I do. Anyway, so we're down here. We want to recenter this. So we have to come in and go into the SWR plot again. And again, this is kind of an iterative process. You have to guess. I happen to know that the right numbers that we want to see are 7.6 and 7.6. So enter those into that field, rerun the SWR plot, and now we have a display that is centered. Now, here's an interesting thing about a dipole. We've just built a dipole, and at resonance, we're at 84.5 ohms. I thought dipoles were 50 ohms. Well, they're not, and I'll show you exactly what affects the SWR and the curve. This is why everybody has told you since day one, don't pay too much attention to your overall SWR, because if you have a dipole up at 60 feet, bare wire in the free space up there, your dipole, your best SWR might only be 1.7 to 1 if you're feeding it with a 50 ohm coax. It's the way it is. But let's take a look at what happens. This is the fun part of all of this. We can now see, all right, what happens to my SWR if I were to lower this antenna? I don't have a 60-foot skyhook. All I have is a 30-foot skyhook. So I'm going to lower one side of that, if you noticed. And I'm going to lower the other side of it so that we're horizontal. So now we have a 30-foot high dipole. You also notice that the SWR window went away because it's no longer valid. But let's rerun it again and take a look at it using the same parameters. It remembers it. It's got to think about it depending on the speed of your computer. Now, a 30-foot high dipole, notice that the frequency of resonance has changed. The ground has affected the resonant point of your dipole, but at resonance, it is now 1.35 to 1. So a lower dipole actually can give you a better resonant point than the or SWR than a higher dipole.
It's also a narrower bandwidth too, isn't it, Fred?
It's
higher Q.
Yeah, that may be an anomaly of the scale here, but yeah, it does look like it's lowered. I'm going to show you this part of this slide. Okay, so here's the two that out of the slideshow. You can see definitely that it does look like it's narrowed considerably, but the span has stayed a constant. And again, this has something to do with the scale. I'm not sure that if we were to rescale this, it wouldn't be about the same bandwidth. So what you have to do now is you have to go back up and we'd have to play with this. Okay, now as you can see, we're short. Now we have to go length, or we're too long rather, and we need to shorten the antenna again. Maybe you'll go to 66 feet and so on. But what I wanted to show you is that in free space, we have, if you notice, and I probably should have mentioned this before, go over here to ground type. Hopefully you have real mini neck clicked. And the ground description is his default description in Siemens and the dielectric constant. So what we want to do is we want to change the ground type now. Let's see what kind of an effect it has. So go click ground type, and another window called ground type should show. And I want to show you, let's put this antenna up 1 billion feet, and it's in free space now. And we're going to click that. Our SWR goes away. So let's go over here to click SWR, reprint that. Now, this is a free space dipole. And a free space dipole has an impedance at resonance of about 72 ohms. You may be used to the typical formulas, the 468 divided by F, all right, for the overall length. But understand, this is the point of resonance for a free space dipole, and it's not going to be You know, for a free space dipole, you're going to be looking at only 1.4 to 1 SWR at resonance. Any questions so far? Are you able to keep up? Okay. Now, just to show you the effect of and the power of this program, I just kind of wanted to show you. Let's go back up here to this insulation type. So far, we've been using bare wire. We've specified bare wire because 1 is the dielectric of free space and 0 thickness of your insulation. So I want to go to put a PVC wire in here, and this is going to be, I happen to know, 4.7 dielectric constant, and I'm going to make it a pretty thick insulation, let's say 0.05 inches of insulation. And let's remember, we're still in free space now since we changed it over here, but we're looking here at 7.04, and let's rerun our SWR curve. By golly, insulated wire makes a difference. So the insulated wire actually shortened us. And I, just as anecdotally here, I had down in North Carolina, I had a dipole that the center was 30 feet away from a tree. And normally that would be a 33-foot leg on each half of my 40-meter dipole. I put it up with insulated wire, and the length turned out to about 30 feet, and it fit perfectly. So sometimes that's very useful. You can actually go ahead and do it. Anyway, let's return our dipole back up to 60 feet now. And we're going to go up here, 60 feet and 60 feet. And let's go back to, yeah, I can't, you guys are covering me here, but let's go back to 1 dielectric and 0 thickness there. Click anywhere on the screen and we should do that. So the next interesting thing here, of course, is what does our pattern look like? We've looked at the SWR curve, and we want to go to the far field plot button now. This is where really all the fun, more fun begins, other than just SWR. But now we're going to have to do this. We want to choose we're going to look at the azimuth display first. So choose your plot type button. Let's go to the radio button and click on azimuth. This is kind of looking at the pattern as looking down at the antenna, if you will. Click OK. And now we have to choose an elevation angle because that pattern, the azimuth pattern, changes depending on what angle we're looking at above the horizon. So we're just going to arbitrarily look at it at a 20-degree angle above the horizon. Click OK. And now you can click far field plot, and by golly, looks something like a dipole. The free space dipole actually goes down to 0 over here, but the ground effect again may change this. So we've got a pretty good looking thing. If we want to now take a look at the elevation, here's what the elevation looks like. We're going to have to go into the plot type, elevation, click, do that, hit the far field plot button again. And that's something wrong here because what have I done? Without going into that, I'm going to show you what it should look like. So this is our elevation angle when we go into that screen. Now you can go around and click on anything. Again, all of the information that you are interested in is down here. So for DX, we might want to concentrate on our antenna design to be somewhere in the 5 to 10 degree angle. Let me just see if I can figure out what I did wrong here on this far field plot. Did a free. Oh,
You need azimuth angle?
no. What I see, this is actually the pattern in free space. Let's go back to the ground type. We want to go to a real ground now. And let's use a mini neck ground. I'll explain what that is in a few minutes. Click that. Now our far field plot is going to look something like that. In free space, the elevation angle here is determined by an interference pattern from the dipole and reflections off the ground. You can kind of play with this. You can change your antenna height. And let's just kind of do that right now. I'm gonna put this up at say 300 feet. You just spent a lot of money. And Lavelle is going to help you put up your 300-foot tower. Let's do that. We're going to do the far field plot. Now you see, this is the turkey feather pattern. And what you're actually seeing here is you got a very, very low angle of radiation, maybe about at 7 degrees here, and that's your peak. But look at what's happening here at 12 degrees. You've got a big null. So if you kind of look at this and you've got an antenna up at 300 feet, the big guns, when they have multiple stacked antennas, they'll very often tell you that their lower antennas hear better than their higher antennas. And this is why, because there are, in the elevation patterns, there are these huge nulls as you start getting higher and higher. But what I wanted to do is I wanted to go down to 30 feet. Let me just make sure I'm on schedule here. So let's go down to 30 feet again. And let's kind of look at what that pattern looks like. And this is what you got to do. This is the teaching aid that I was talking about. What is critical about my design? So here's what it looks like at 30 feet. One thing we can do, by the way, we can go in and superimpose a few arrays over this. So we can look at, for example, add trace. All right. Now I'll show you what that comes up with over here. I have already saved a trace of a 40-meter dipole at 60 feet. We click that in, put that in, and now the two traces are together. So this is what your pattern is going to look like in the elevation view at 60 feet. This is what your pattern is going to look like at 30 feet. And boy, you know, at the very critical DX angles, you can see there's a 5 to 6 dB. It's like adding an amplifier to you. Height matters. The way you do that is file, you have to basically save the trace, and it will bring you back into the menu over here. You name the trace and save it that way. And that's how I was able to get some of these things. I could add another trace over here like that. Here's the dipole at 15 feet. I don't know if you can see that, but there's a little green arrow. Everything's going straight up in the air. And a little comment, by the way, everybody says, oh, my antenna is NVIS. You know, the ionosphere doesn't reflect anything up here. The ionosphere bends. It's not a mirror. So when you're shooting straight up, you're talking to the aliens up there, which maybe Kurt's pretty good at, but the rest of us are not. So yeah, NVIS, you don't want it. They don't work.
Fred,
Yes, sir.
on this total field diagram that you've got, besides the file name, is there anywhere on here that it shows the elevation of your antenna? Because I don't see it if there is.
Yes, the elevation, you go to the wires menu up here. All
Okay.
right. So the Z height, this is the height of your antenna at end 1, which is over here.
Right, I got that, but on this 2D plot of the backyard dipole, yeah, and that one there, is there anywhere on that diagram where it shows the elevation of the antenna?
This is the elevation in the antenna in the outer ring, if you will, the black ring, if you will, is defined by the wires, sources, and all of this stuff over here. All right.
Okay, well, since I was late, I have no idea how to get the wires and the sources. I finally got the 3D of the antenna, but I'll find out later how to get the wires and the sources screens up.
Okay, so to get the wires screen, you just press this button here. And the sources screen, you just press this button here.
Okay.
And then you want to go in, and these are Cartesian coordinates. Okay, so where
Right.
we stand right here. End one of the wire is at 0, 0, 30, x, y, 30. And the end two of the wire over here is at 0, 68, 30. So enter those numbers. Excuse me.
Well, now on your three-dimensional drawing of it, where the red circle is there on your antenna itself, is that the feed point then?
Yes, this is the feed point of the antenna, and we're
Okay.
we're specifying that by we want to put it in wire number 1. There's only one wire in this model.
Okay.
We want to put it at 50% of the overall length from end 1. Percent from end 1, and that's
Got it.
I specified 50.
50% from the other side also, and you've got 6 segments from.
Well, we specified 11 segments. That's up here. Okay.
Right.
It put the source in segment number 6, which is, if you think about it, that's the center of the dipole. And then you have 2 other parameters over here. One is called phase. When you have more than one source in an antenna, you like a phased array, for example, you can specify the phase of each source, and then also the type of each source. For simple designs, we're going to use current, I, the letter I. There are voltage. It doesn't really matter in simple models if you use a voltage or a current source. These are split sources, and I actually, if we have time, I'll get to that in a second. Any other question, Warren?
So Fred, I have on occasion had the actual position shifted. Is that because I don't have an odd number of segments?
That is correct. So you want to be, if you don't have an odd number of segments, it's not going to be able to put it in the middle.
Got it, thanks.
So the actual position will show you something different than 50. So if you go over to the wires menu and choose 11 segments, then it can find a segment that's in the middle, in which case you should see something like this over here.
So I guess I have a question and maybe an observation. So when you're running this at 60 feet, it appears that it has, shoot, I should have prepared it a little better. If I put it at 68 feet for each end and look at the far field plot, it looks like the lobes are the most projected and higher gain, and there's no central increase. So if you were to run them both at 68 feet in elevation.
Well, don't confuse the length of the antenna. So 68 feet is the length of our antenna.
I was doing the Z's.
Yeah. So
if I ran them at 68 feet in elevation and looked at the far field plot, there was that no straight up vertical, no bump. If you run it at 70 feet in elevation, you can see that hump in the very center. So that's vertical going straight up. If you run it at 68 feet, it seems that the lobes are the most loby.
and go even higher. You know what I showed you. You know, you can go up to 300 feet and you start seeing that turkey pattern. All right.
So is that what you're trying to achieve? Essentially, like with a dipole, is you're trying to get the most gain off the lobes and direct that signal, let's just say north and south versus north-south and straight up into space.
The whole purpose here is to design the best antenna for what you want to do given the space you have available.
Gotcha.
All right. And that's really what you want to do. For example, if all you want to do is stateside rag chew, well, maybe you want to optimize your antenna for the elevation maybe between 40 and 30 degrees. If, however, if you want to talk to Bangladesh every morning, you need to optimize your antenna for these elevations down here.
So a lower takeoff angle to get that skip further.
Exactly.
Gotcha.
Now, in general, all right, and through probability studies, we understand this, but in general, the lower the frequency you get, the shorter the skip. So when you're down at 10 meters, you know, you really want to be down to 5, even lower angles. 10 meters, you know, you can get when the band is open, I should say, you can get really low angle skip. Whereas on 40 meters, you don't get that. You know, the typical 40 meter DX might come in at 20 degrees. So again, it's an advanced topic, but I could show you the probability of where these signals are coming in and what I did in the article that in Q Street, I showed basically you can design your antenna based on the probability of where the signals are coming in. Say the highest probability of signals coming in from Europe on 40 meters might be 20 degrees. Well, let's design an antenna. Okay, look, I don't have a 60-foot tower, all right? What's important to me? Is it going to be better for me to put a vertical up, or is it going to be better for me to put a dipole up? If I want to work Bangladesh as opposed to New York State. That make sense?
Yes, I appreciate that. Thank you.
All right, let's see.
What would I do with this if instead of a center fed dipole, I wanted to do an end fed dipole? How would I move that feed point on this diagram here?
Well, it's actually very easy. You just come up here to the sources diagram.
Oh, okay, that makes sense.
Okay, and let's just say we want to put it 10%.
And then the other one at 90.
And you know, so something happened to my view. Oh, I'm at 300 feet here. So we want to go down to 30 feet again. And you see how the source location changed to 10%?
Sure. So what's the difference between the specified position and the actual position then?
It is a limitation of your freebie program. You can only put in 20 segments, okay?
Right.
So the program is going to put in the source in the middle of the nearest segment that you specify.
Got it.
Because it's discrete, you cannot put it exactly. Let me just show you. If I change this, you guys can't do this, but let's change this to 33 segments. All right, and it'll give me a warning as, whoop, no, you can't do that because the segment's too small and the program crashes. But let's go to say 21 segments and watch this number. Yeah, I'm still
20. You're running the demo version too, it looks like. It's 20.
I guess I am.
Yeah, what it
Yeah,
says on your screen.
It is. Okay, so all right, so I can only go to 19. Here, I thought I was running the real thing. It doesn't really matter, but this is the only place it does matter, actually. But you notice now with 19 segments, it got a little closer to my specified 10%. Let me just do that again. So I specified 10% and I'm only at 7.89%. I'm going to go back here to 11. And you see, with 11 segments, it can't get quite as close. Does that make sense to you? Now, your question was end-fed designs. You really can't do an end-fed design. There is a special area in here that will allow you to put the source. And that has to do with this split types that I was talking about before. I'm not going to get into that, but in this session, but for end-fed dipoles and things like that, there are some special considerations.
Now, why is 10% chosen and not 0% from E1?
Because that's what I specified. We can go down here and do 0%, okay, and it's going to get closer. But you see this, it comes up with a warning at 0%. Source 1 is on an open end. So we're going to get lousy numbers if we start doing that. An end-fed dipole, as I say, there's a way to handle it in here, but we're not going to get into that at this point. What I wanted to show you, though, again, you can kind of, let's see. I lost my spot here, bear with me. So I wanted to show you, let me just go to this slide here. The question often comes in and says, okay, what if I bend my dipole? How does an inverted V look like in comparison to a dipole that's straight out? We're gonna build an inverted V here in the next couple of slides, but I'm going to jump ahead here. The blue curve here is your straight dipole, and the black curve is your inverted V. And if you notice, yeah, you might lose a dB. And this is a 90-degree catenary angle at the top. So it's about as bad as you're going to get in any inverted V. The closer to horizontal you're going to see very little difference in there. So the beauty of a dipole is that they want to work. Okay, you can bend them any which way. You can make your own models, and you'll see exactly what's going on. This is just an example of they're not all that critical. You're going to get good performance. What is critical is how high you make this. You do want to get it as high as possible. You've been hearing that since you first started thinking about antennas. You got to get them up in the air, and that's
slightly related to this. As you change an angle at your feed point of a dipole, doesn't that change your input impedance then also?
Absolutely.
Okay.
And let's just use this as an example. I'm going to go back to the 50% feed point, and we're going to run an SWR plot. Now, our SWR is 1.35, not too far from the theoretical 67, but of course, we're only at 30 feet. Remember, the SWR got better as we dropped the dipole. So we're going to take this and let's just do an off-center feed. How about that? You've heard a lot about off-center fed dipoles. Let's make it at 40%. And we're pretty close to that 40% point. Not too bad. And let's rerun rerun it. Well, okay, the frequency has changed a little bit, but it's not too bad. You could actually see that the pattern hasn't, it's not terribly critical that it be exactly in the center. Now, we're going to do a far field plot. This is the 30 feet. I wanted to point out here that you see this little curve, this purple curve on the top? That's showing you the current distribution on your antenna. Rule of thumb, you want to get the current distribution of your antenna up as high as possible. It's the current that's creating the radiation to a great extent. Notice down here at the ends, there's no current flow. It's like putting one wire into an electrical outlet. No current flows at the end. It can't. It's got no place to go. So the maximum current flow is usually in the center of the dipole. And what we have here in the SWR plot, I covered it up here. But in the SWR plot, you can see now that, well, we've got that. And you can experiment with that. It's going to affect your SWR. If you want to see what this antenna does on other bands, you can take your SWR plot. I'm going to get rid of this because it's covering everything. But you can take your SWR plot and you can scan from that to 28 megahertz. And since I'm going to go in 100 kilohertz step, otherwise this will take forever to run. And you can just do this. And you see my computer is doing all kinds of things over here. It's calculating at every frequency. Now, here's what we have. It looks like we have a resonance around 6.8. We have another semi-resonance over here at 14, another resonant point here at 21. So you can see kind of off-center fed dipoles, you might actually get some resonant points. Lousy SWR, but they are resonant points, so they can actually work. Anyway, I am getting a little off subject here. So we're going into session 2, and but the couple of points that I think are important to understand, that EZNEC wires cannot be bent. You can draw them at angles, and you can put multiple wires connected to each other to simulate a bend, but each wire that you put in can only be straight. Connections can only be made at wire ends. You cannot take a wire and try and connect something in the middle of that wire. You can only make connections. You could put sources in the middle of the wire. You could put loads in the middle of the wire, but you cannot connect another wire except at the ends of each wire. So we're limited to 20 segments here, but I wanted to just kind of show how to build an inverted V. There's a couple of different ways. There's an easy way and there's a hard way, and I'm going to start with the hard way here. So tell you what, I'm just going to go through the slides here if it's because it'll go a little bit faster for me. So what we want to do is we want to make a very, very short segment. Warren, this was what I was telling you about before. You want to make a tiny little segment. So we're going to go into the wires menu. We're going to put in a wire from -1, a 2-foot long wire. It's going to extend from -1Y to +1Y, and we're going to keep it up at 60 feet. And you notice it looks really, really tiny up there, and you may want to go and zoom in that. I've changed the number of segments here to 3 so that we don't go over our limit. But we now have a very short little segment in there. It's going to resonate at some unknown frequency pretty high. And the source, again, we put here at 50%. So I zoomed in on it. You can kind of see this is -1, this is +1. And now we're going to add some other wires to it. So wire number 2, we're going to connect wire number 2 over here at this end, and we're going to connect wire number 3 at the other end, and we're going to take it out to the dipole length. So what I've done here is I've gone from 0, -1, 60, because 60 is our height in this example. So we're going from -1, and the other end of that wire is out at 0, -34, it's way out here, 60. And again, if all you got to do is click on these blank spots over here, and it'll just copy what's above it. So if you want to stay in number 12 wire and bare wire, it'll just continue on doing that. So we got our 40-meter dipole back. If we took a plot of that, this is what we would see. We'd be about 7.1 megahertz. And I did that by carefully selecting the length. Now this is 68 feet again, -34 to +34. So we've got an overall length of 68 feet from this point to this point, which is what we had before. So let's take, this gets a little complicated now, but we want to make an inverted V out of this. So what we're going to do is we're going to take this wire and we're going to rotate it down by 30 degrees. Let me show you how that's done. So we want to go over to the wires menu, Click on wires. You'll see a button under there that says wire. Another pull down menu comes up and you should see rotate wires. So we want to come in here when this is the menu that should pop up. First wire to rotate is number 2 because we're going to rotate this wire number 2. And the last wire to rotate is wire number 2. We only want to rotate one wire here. We want to droop it by 30 degrees in the counterclockwise direction. Now, rotation axis, it's going to rotate around the x-axis here. So we're going to rotate it like that. And then the actual axis is we're going to rotate it around that particular end at -1. So that's wire number 1. That's the center, the tiny little center wire. We want to rotate it around N. And you can do it over around the coordinates or the center of axis. And I'll tell you, I always screw this up. I don't know if I'm rotating it clockwise or which axis. Sometimes for me, it's just a trial and error. But click OK, and you'll see that wire number 2 droops down now by a good 30%. 30 degrees, I should say. We do that again. You go up to wires, wire, rotate wires. Now we're going to rotate wire number 3, the last wire to rotate number 3, because we only want to rotate one. Go over to 30 degrees. Now we want to go in the clockwise direction, the other way, still around the x-axis. And now we want to rotate around N2 of wire 1. Don't worry if you're not following all of this, because it does tend to be a little confusing. And frankly, I always screw it up. I always end up rotating it in the wrong direction. I have to go back and say, okay, it went up rather than down. Let's try clockwise instead of counterclockwise. If you're smarter than me, maybe you can go ahead and get it nailed initially. But anyway, you can rotate your dipole now, and just by reorienting it. And this is our inverted V, and that's our inverted V SWR curve. Now, the alternative method uses split sources. In this method, what a split source is, you can take a junction of 2 wires and say, I want to put a source at that junction. In the case of an inverted V, that junction would be the center point of your dipole, where it all bends. So the easy way of doing this is just to draw 2 diagonal wires and then put a source at the junction. And what the program has to do is it has to split the source, and it has to put half of the source in the segment to the left and half the source in the segment to the right. So you can just kind of draw it that way, use a split, a split source. This is split current, I. There's a split V, voltage. And again, in this design, voltage and current, it's not going to make any difference to you. So, pardon me. So these are the numbers that that we ended up with before. You can go, I'm going to send out this presentation so you can go through all of this and just do all the numbers yourself. But that's pretty much it. Now, vertical antennas. Does anybody have to go? We're running a little bit over time here, I think, but we got 5 minutes to go. And I just got a couple of slides here, but I just wanted to kind of introduce you to grounds, and I promised to tell you about this mini neck ground, exactly what that means. Go over to the let me pull it up here. Go up to the open file. It's going to say description has changed. I don't think we really want to save this, but let's open Vert1, V-E-R-T. Double click on that, and now we have a vertical.
Where are you getting these files from? They're not on my computer.
Yeah, well, you have a limited set of files, but go to the open button, click on that, and another window with your files should show up. I have a lot of files, you know, because I've been playing with this for years, but you want to go down your file. You should see this folder, this file called Vert1. You want to just double click on that or single click on it and then hit open.
PC documents.
It's under Documents, EZNEC, ANT. A-N-T.
Yeah, we're talking about documents. Because mine's opening up downloads where I had downloaded EZNIC file for Hexbeam.
Okay.
So it's not going to the default location. Okay, there's documents. EZNIC 6.0.
Or just search for Vert1.
And I got the last.exe. Yeah, just do a search. Vert1. Go ahead. Don't mean to hold you up.
It's okay. So anyway, Vert1 just is this. Mine came up at 7 megahertz. I don't know if I have modified that. And we're back in meters now because we reloaded everything. But that's we're not going to do anything. I just kind of wanted to show you when it comes to verticals. Let me get up to the right spot here. So when we get into the verticals, you see the source is down here real close to the bottom. I specified, I don't know who asked that question. I wanted to put it all the way down at the bottom, but the closest it could get, because in this model there's only 10 segments, the closest it can get is about 5% from the bottom. And again, you can make that, if you get the pro version, you can get more segments. You'll find it's not all that critical though. You can't see the antenna in here. I think if we move it a little bit in one direction or another, you can get a clear view of what the antenna looks like. It's just a wire. And let's go in there and reset. Now, we want to take a look at this SWR. So we're going to enter some of the same parameters to sweep the SWR. Now, you notice down here, this is half of the curve. I'm not going to bother recentering this again, but this is what it would normally look like. Now, notice for the mini neck ground that we specified, you can, in the case of a vertical, a mini neck ground, you can kind of say, okay, I've done my work. I've taken ground radials. I've taken 120 ground radials. That is a perfect ground in the near field. Within a quarter wavelength, that means the efficiency of your antenna is 100%. You're not keeping the earthworms warm, as they say. So notice that this isn't 50 ohms either, though. Now all of a sudden we're down here at 37 ohms, and actually the radiation resistance, if you will, at this point is theoretically, over a perfect radial system or a mini neck ground, it's 32 ohms. Now, Laval, if you recall what we were talking about, let's see how close you are to a mini neck ground and what you've done. We have a radiation resistance called R1 here, which is about 32 ohms. R2 is the sum of all your little ground radials. You know, this is your ground resistance, your local ground resistance. And R3 is the resistance of your antenna wire, which we can normally just kind of ignore. So the better your ground here, the better you're going to be towards 32 ohms. But you're not going to be, again, you're not going to be a, I keep clicking the wrong spot. You're not going to be a perfect 50 1.1 to 1. Your best is going to be about 1.38, 1.4 to 1. So again, don't get too hyper about the SWR, as they always say. So this is an important thing to, I've only got a couple of slides to go here. The near field ground is the ground within about a quarter wavelength of your antenna. You have control over that. You can put in radials. The near field ground determines the efficiency of your antenna. You're not heating any loss in R2. Everything's going into the radiation resistance itself. So the efficiency is determined by your radial system. The pattern, your elevation pattern, that you've all seen elevation patterns looking like this, that's determined by the ground resistance in your neighbor's yard, or a mile away or 2 miles away. You don't have any control over that. Sorry, but you could put in all kinds of ground radials. You'll have an efficient vertical, but this radiation pattern, this elevation pattern, if you will, is determined solely by the distant ground resistance. If you happen to live on the seashore, you can see you've got a perfect little antenna here for DX, a 0 degree angle. Everything is looking good. You've got 5.5 dBi gain, but in the real world, you get this little suck out here, and that suck out is caused by the far field ground impedance. And we're looking at, notice the scale here too, that the outer ring here is minus 0.04 dBi, whereas the outer ring here is at 5. The far field ground resistance really makes a huge difference in how well your vertical is going to work. But that said, if we have to compare verticals to dipoles, here's our dipole at 60 feet, and the inner circle here is our vertical at 60, at ground mounted with a mini neck ground. Boy, why would I ever want to use a vertical? Well, if you can get your dipole up at 60 feet, by all means, you don't want to put up a vertical. But let's say you only could bend it up 15 feet and you want to work DX. You take a look at this, down here at the critical DX angles, the vertical actually beats the dipole. So again, you can just kind of play to see what your installation looks like. Now, elevated radials, to make a long story short, elevated radials can make a system look like a mini neck ground. They're a whole lot easier, but they have to be tuned. Even if you can only get them up 10 feet off the ground so you don't strangle the reindeer, you can get very good performance off an elevated radial system. This is why my 80 meter vertical, my full size 80 quarter wave vertical on 80 meters, I have elevated radials rather than doing what Laval did and putting in all kinds of radial wires. And here's the pattern. It looks a little bit different, but you notice it's only about 0.13 dBi, which is comparable to what we had before. And you notice with even just 2 radials, it's almost a perfect circular pattern. And the radiation resistance is very similar to the perfect, it does have a slightly lower feed point impedance than the ground mounted radials. And that's actually it. So, you know, the whole purpose of this is just to show you what some of the buttons do. I think it's a great training tool for learning what's important with antennas and what isn't. Play with it, you know, bend your antennas, take a look at it, raise the height, compare it to a vertical in the backyard. And when you really get good, you can do what Warren did. There's all kinds of pre-made antenna patterns out there, files. You can get hex beams, you can get, you know, 6-element Yagis, you can get, there's thousands of them that guys have put together. Go take a look at it, just play with it.
Question, Fred.
Yeah.
Inverted V. I didn't do the rotate. I just lowered the ends on the Z axis. Does that have similar performance?
Yes. Well, when you just lower the Z height, you're actually, if you think about it, remember Mr. Pythagoras, you're actually changing the wire length too.
Okay.
That's why
I
you
didn't
want.
think it changed.
Yeah, it will. Think about it. I mean, you know, now you're going down a hypotenuse, all right? You're going straight down the vertical Z height. So the length of the wire has increased now.
Okay, so that forced that change in the wires diagram apparently then,
Right. Well, that's going to
to the
change.
table.
Yeah, that's going to change your resonant point. Okay. If you do that and you redo this SWR, you're going to see your resonant point is way off. You're going to be a lot lower in frequency than you think.
I don't think I noticed that the wire length changed in my wires table. That's why I thought it might have worked.
Well, think of the geometry. Okay.
Sure. No, I know what you're saying.
That's why you really want to do the, you can calculate that point. Yes. You know, go into, you know, your trig functions and you can calculate that point. I find it easier to keep the wire length the same and just rotate the wire.
Yeah, absolutely. Live and learn.
Anyway, just play with it. My hope is that you guys will get better than me in this, and you can answer some of my questions that remain on what we do here. So 73s and